The quantum harmonic oscillator is an example for a potential with which we can solve the Schrödinger equation analytically, without the need for supercomputers. In the one-dimensional case, we have a parabolic potential that looks like this. We can imagine this as a particle that is confined to a one-dimensional box, and the further it moves from the center, the more it gets pushed to the center. In classical mechanics, a harmonic oscillator could be represented by a mass on a spring, moving left and right, so that the corresponding differential equation looks like this. A spring exerts a force proportional to its elongation according to Hooke's law. And since force is the gradient of a potential, we see that the potential is proportional to x squared. So that is why we call the x squared potential we will use in the Schrödinger equation a harmonic oscillator. The Schrödinger equation is an eigenvalue equation, where we have the energy operator, the so-called Hamiltonian, on the left, and its eigenvalue, the energy, on the right. The total energy is given by kinetic energy and potential energy, where the kinetic energy is p squared over 2m, and the potential energy is proportional to x squared, as we saw earlier in this video. The factors here are constants that do not change the nature of the potential. If we plug everything into the Schrödinger equation, it looks like this. Remember, we are dealing with quantum mechanics here, so the position operator x and the momentum operator p cannot be exchanged like in classical mechanics. Instead, we have to deal with an additional term, I times h bar. It is important to keep in mind that the Schrödinger equation is an eigenvalue equation. Therefore, it is possible to obtain the eigenvalue as well as the eigenvectors. We can claim to have solved the quantum harmonic oscillator if we know the wave functions as well as the corresponding energies.